Okay, so in the last video, we talked about t-distributions and what to do if you're sampling from one population and what to do when you're sampling from two different populations. And so what we're going to talk about is paired data. And our paired data is a scenario where it seems like there are two populations involved, but the reality is we can really treat it as like one population. So I'm just gonna go ahead and write up a short example here. Uh, let's suppose five people uh, five people go on a diet, uh, and we want to see if there's significant loss in weight. And let's go ahead and make up an alpha because we need one, right, in order to be able to judge this. So we let our alpha be 5%. And by the way, five people is really too small of a sample to really actually do a study. So this isn't a very realistic scenario, but it's just to make a point, right? So we have five people, they go on a diet, and we want to see if any weight loss that's experienced through all of this is statistically significant. So what we end up with then is like a before and after table. So let's say there's before and after diet. And let's say beforehand, their weights are 160, 170, 120, 128, 110, 210. And let's say after they were 150, 168, 130, 110, and 208. All right. So we could look at this data and then we could try to predict whether or not there's a statistically significant uh, decrease in weight. And so the way we would set that up if it were a two, uh, if it were a uh, difference of means between two populations would be right. We'd have mu be this you would get a mean and a standard deviation from the before people. You would have a mean and a standard deviation from the after people. You also, of course, uh, have an observed mean and an observed mean for both populations, and you would say something like the alternative hypothesis is that mu b minus mu a is greater than zero, right? That would say that, well, they weighed more before the diet than after. And your null hypothesis will be something like mu b minus mu a could be zero, right? And that would mean that there could be no difference, right, in their diet. Now, this isn't. This is actually not correct, right? So let's make that clear right now so that no one's confused. This is not actually how we should think about this problem, but it's subtle as to why that's not correct. So let's go ahead and kind of paint the picture of what's going on here. When we do two population samplings, right? The whole idea is that, we have two populations, we pull a sample from one population, we pull a sample from the other population, we check the differences between them to see if there's any statistically significant difference. So maybe over here is people on diet and people not on diet. Right? And so we would reach into one group, pull out a bunch of them, reach into other group, pull out a bunch of them, and then we would take, we would find the means, the standard deviations, and blah 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 of both of those groups, and then we would compare them to each other, and we would see if there's any difference. But that's not really what's happening here, right? And which is why this isn't exactly correct. Um, we didn't just pull 5 random people on this diet and 5 random people off this diet, right? We pooled 5 random people, but we measured those people both on and off the diet, right? And so it's not true that these things were sampled independently of each other, right? There's a natural connection between the people on the diet and the people off the diet. And so, really, what's going on here is that there's one group of people, we sampled 5 of them, right? And what we're looking for, and what we're actually wanting to measure, is the relevant variable is changing weight. Say, right? So really there aren't 2 separate groups of people. There's one group of people, and we go in, pull them out, and then we measure the changes in weights. So if we go back to this original column here, we could see what the changes in the weight are, right? So we could see that this is -10, this is -2, this is +2, this is 0, this is -2, right? And so really, what you have is a sample of size 5 with a sample mean of well, what does he get? -10, -2, 2, 0, -2. So a sample mean of the differences is -2.4. We can see that here. And the sample standard deviation is 4.5607. So the sample standard deviation of the differences is 4.5607. And of course, I could pull this open and just read it, right? If I so felt compelled. Now, in most of the homework problems in Infinity, this step has been suppressed. So you may or may not be given raw data, but they'll compute all the sample statistics for you, so you don't have to do this part by hand. And this we already did in chapter 1, and it's not particularly hard, right? And so your null hypothesis then, an alternative hypothesis, your alternative hypothesis is that the change in weight ought to be negative, right? It should be that the average weight change is less than 0. Right? That we're trying to see if the data works. We want to see if, on average, the mean of the differences in weights is less than 0. And then the null, of course, is that it could be 0. Right? And so if we want to test this hypothesis, and again in real life, you probably should not test this hypothesis at all, because your data is way too small to really do anything realistic with it. But this is just a thought exercise more than anything else. So we have our average of negative 2.4. Sorry, wrong one. There's only one variable, right? The one variable in question is the differences of, it's a changes in weights. So we measured 5 different changes in weights. Uh, the average change in weight was a loss of 2.4 pounds with a standard deviation of 4.5607, and we're comparing it to 0, right? Our null hypothesis is a comparison to 0. So over here, we let this be 0. We said our alpha was 5%, and our alternative hypothesis is that the actual difference is less than that 0, and so we get a p-value of about 0.15, so 0.15228. So let me go write that down. Is 0.15228. And so let's be very clear about what this p-value means. And what the p-value means is if there is no difference in people's weight before or after the diet, and remember that's our null hypothesis here basically, right? That there is no difference. So if there's no difference in people's weight before or after the diet, the probability we weigh 5 people and find a average difference of at most negative 2.4 pounds is exactly the p-value, 15.228%. That is what the p-value measures after all, right? And so that's not that unlikely, right? So what we're basically saying is, look, just by random fluctuation in people's weights, just like a 15% chance you're going to see this weight fluctuation, uh, even if the diet has no effect. It's like, all right, then that information probably tells us very, very little. And of course it doesn't, right? These differences are not that big, and the sample size is only 5. So it's not shocking that there's no statistical significance here, and it's very far above the 5% alpha that we would have required of ourselves to have statistical significance. So um, there are other examples like this. Like a common example that you'll find in textbooks is couples. If you have married couples and you compare the spouses to each other, um, according to some metric, whatever it is, uh, like if all of the couples in question say were men women couples, and we took all these couples and we measured some metrics in the men and we measured some metrics in the women and we compared the difference, this is not the same thing as gathering, say, 20 random men and 20 random women and then comparing the differences. That doesn't have the same effect as taking 20 man woman couples and then measure their effects because they're not sampled independently of each other. They're connected by the fact that what you're sampling is not random men and random women, but in fact random couples. So whenever something like that is being done, where you're not sampling two separate things, you're just sampling one thing that happens to have two parts to it, that's when we use the pair differences. So hopefully that helps clarify that. And well, we'll talk to you later.